So 2.1, example one from Math30-1, we get into some actual radical functions. And we've already done this one. This was in the instructional video. This is y equals root x. So we see everything that we would expect. Talking about the domain and range, just so that we do see maybe a different way of presenting that. I'm going to give this with interval notation. So x would exist from, oh, I messed up already. Good start, good start. We'll try that again. X is going to exist. We need to put a square bracket around 0 because it can be 0, and it's going to go all the way to positive infinity. And x is an element of the real. That's our domain. Our range is very similar. Y is going to go from 0 to infinity, and it also is going to be an element of the real. Now, with transformation, transformation language, I do hope you can identify that in B, because we're subtracting 2 directly from x, we're going to shift that graph 2 units to the right. In C, because I'm subtracting 3 from the entire function or outside of the radical, I'm going to move that graph 3 units down. But we should expect to see that in our table of values as well. What's a little bit weird about this, I would say, is that when we look at our second function, the person who made this table of values just kind of magically knew to make those values 2 larger. And I would like to reiterate that the reason that this makes sense is because we subtract 2 from x before we take the square root, all of the numbers in this list are 2 more than a perfect square. So if I put 2 in for x, I subtract 2 first, the square root of 0 is 0. If I put 3 in for x, I subtract 2 first, the square root of 1 is 1. 6 minus 2 is 4, root 4 is 2, 11 minus 2 is 9, root 9 is 3, and so on. And what that does for the graph is it literally just picked up that y equals root x and shifted it 2 units to the right. Now, if you didn't have that graph available to you, when you see that y is equal to the square root of x minus 2, you should look at that radical and understand that the inside, the radicand, must be greater than or equal to 0. We can't take the square root of a negative number. And when I manipulate that, I get that x must be greater than or equal to 2. Now, that's our domain. If x is less than 2, we take the square root of a negative number, and that's not permissible. So for my domain, I'm going to put that x exists with a square bracket on positive 2, but it does go up to infinity, and x can be any real number within that. For y, when I put 2 in for x, I still get 0 because the square root of 0 is 0. So looking at that graph, it's a little bit clearer, I think, to see that that y value is going to go again, or similarly to y equals root x, from 0 to infinity. Now, one of the reasons for that is because x minus 2 is entirely inside that radical can only yield the smallest value of 0. And so even though we're subtracting 2, because it's on the x, it doesn't affect the y values. It just kind of affects where they happen. So y is still going to be our kind of standard range of a radical, which is from 0 to infinity and any real number within. Now, for C, they throw a little bit of a curveball at us. And I'm going to put the equation up here. It's y equals the square root of x minus 3. This is why I close my radical like that. It helps me to identify what's inside the radical and what's outside the radical. Oop, I went too far there. You do not have to do that, but sooner or later, if you're not careful with it, you're going to think that 3 is inside. Now, for the domain, before we even look at the graph, because only x is inside the radical, x must be greater than or equal to 0. And I'm just going to cheat a little bit. That becomes the domain. That's the domain of our function. Range is a little bit harder. And I often recommend students get a graph before you do range. But if we think about what's happening here, if y is equal to the square root of x minus 3, the smallest value for the square root of x is 0, but then I'm going to subtract 3 from there. So the lowest number possible is going to be 0 minus 3, but it's going to be everything greater than that. So my range will be that y exists, and I guess I used inequalities over here, so I'm going to do that again. For y, we're going to say that y must be greater than or equal to negative 3, but it's any real number that satisfies that condition. Now again, this one is a little bit easier because just x is in the radical. They pick perfect squares again. But what's going to happen is I'm going to take the square root of 0 and then subtract 3. So y is negative 3. I'm going to take the square root of 1 and then subtract 3. Root 4, which is 2, minus 3 is negative 1. And we see those points again. Now, students typically like translations more than stretches because adding and subtracting is easier than multiplication. And I really do. I'll show the graph here first. But what's happening in this graph is that we are taking and I'll maybe draw it so that it's a little bit accurate, just so that we can see it. I won't go all the way, but I'll put maybe these 3 and draw it like that. What we've done for this question is we've taken y equals root x in black here, and I've shifted it 1, 2, 3 units down. And again, other than my bad drawing skills, we see that we have the same shape. And that's going to be a really important concept in Math 30, is that if we're doing just translations, so horizontal or vertical translations, we don't actually change the shape of the graph, we change the location of the graph. And that's a really important consideration when we're talking about this information. Very, very similar to what we did in chapter 1, we are looking at a more complex type of equation or type of function, which is the radical.